Welcome to Activity 8.3, Using Forces and Energy to Understand the Magnetic Cannon, and this will be our concluding activity. Now, if you're listening to this and you think I sound a little funny, it's because I've got a cold, so I may sound a little different than I normally do in my videos. So, first of all, our learning targets. Sorry about that. Our learning targets, we're going to explain why ball E shoots out from the magnetic cannon much faster than ball A reaches it. So in the last activity, 8.2, we basically just took a look at why ball E shoots out, why ball A stops when it hits the magnet. Now we're going to start to take a look at why ball E shoots out from the magnet cannon much faster than ball A reaches it. So the expectation for you is just to complete the activity. And if you look on the pages, on page 99, there's a couple tables for you that we're going to be filling out together. And then there's some questions on the next page. So here's something to think about. Why does ball E shoot out from the magnetic cannon much faster than ball A reaches it? So ball A was not traveling that fast. But then ball E really shot out fast. Where did all that energy come from? Why did it shoot out? So, here's a procedure. Summarize in a table what you know about forces and energy. Place a check mark in the energy column of the forces column for each question. So, a couple things to consider. What are forces and energy, and what is the relationship between them? So forces are interactions between objects that can make them change their direction. So if you kicked a football, your foot applied the force to the football. It made the football change its motion or change the direction of its motion. Energy simply is the ability to do work. Energy makes everything happen and can be divided into two types of energy, potential and kinetic energy. We learned that in our last book. So forces cause things to do. And you have to have that energy to cause a lot of these forces. For example, if I didn't have any energy in my legs and I didn't, so I couldn't move my foot, it's not going to be able to apply a force to that football if I kick it. So here's a table. And what I want you to do is, these are some characteristics. So it has direction. So put a check mark if you think energy has direction. Put a check mark here if you think forces have a direction. Then go through the list. An object can have it. One object can apply it to another object. One object can transfer it to another object. It can be created or it can be destroyed. It always comes in pairs. It is transformed. It can be counteracted. It causes motion to change. It is useful for explaining phenomena not involving motion. And it's useful for explaining phenomena involving motion. So as you go through these, go ahead, pause the video now. But what I want you to do is just put a check mark. If you, for example, it is transformed. Is energy transformed? Oh yeah, it is transformed. Then put a check mark. Are forces transformed? Energy. Oh yeah, forces are transformed. Well, then put a check mark. But if they're not transformed, don't put a check mark. So go ahead, pause the video and complete the table. And then we'll discuss what you came up with. All right, so you've had a couple minutes to do this, and it shouldn't have taken too long. Just what is your guess? Hopefully you didn't do it in pen, so that way if you're wrong, you can change your answer. So let's take a look at them. It has direction. Forces have direction. That's why we have the arrows pointing to it. Energy doesn't really have directions. It just depends. Energy is applied to something, and it can be transferred, or it can, go from one object to another. But it can't change direction. An object can have it. An object can't have a force. Forces are applied to things. This isn't Star Wars where you are strong in the force, young one. No, it's not. But energy, objects can have energy. An apple that is you throw up in the air as it goes higher and higher, it's got more and more gravitational energy, which is a type of potential energy. So it can have energy. Forces, an object can't have forces. Forces can be applied to things. So one object can apply it to another. Oops, I just gave you the answer to that. Yes, one object can transfer it to another. Yes, energy can be transferred from one object to another to another. They might say, well, why can't forces be? Well, a force is applied from one thing to another, but that same force is not applied to the next, the next, and the next. Now, so if I push you, I apply my force to you. And if someone's standing in front of you, and you push them, you apply your force to them. It's not my force that goes through you into them. So you can't say, well, technically, if I pushed you and you pushed them, you can't come back and say, Mr. Return pushed, the person in front of me. No, I didn't. I pushed you. You pushed them. So again, objects can't transfer forces, but they can transfer energy. It cannot be created nor destroyed. That is definitely talking about energy. You might say, well, what about forces? Forces can't be created nor destroyed. Now, one force can apply a force to another thing, but it's not in the same sense that it can be destroyed or created. It always comes in pairs. That's forces. It can be transformed. That's energy. We talked about this in our last book. It can be counteracted. Well, that's forces. You can have forces counteracting each other. It can cause motion. Energy doesn't cause motion. Okay, the apple falling down is not causing, the gravitational energy in the apple that's falling is not causing the change in motion. No, the gravitational force is pulling it down, and it is gaining KE as it's falling, but it's not the energy that's causing the motion. Forces cause motion. Now, it is useful for explaining phenomena not involving motion. And originally the book had energy here, but I also put a check mark here, because if there's no force, or if forces are balanced, it could explain why there's no motion, because it's balanced. So we added this check mark here, so it would be both. Did you have both check marks? It is useful for explaining phenomena involving motion, and we had this both, because depending on what you're talking about motion, if an apple is falling, you can talk, and it's getting faster and faster and faster as it's coming down, you can talk about how it's gaining KE as it's coming down. So you can use both energy and forces to help explain motion. So how did you do on this? If you got all these correct, awesome job. If you got a few wrong, it's not too bad. But if you got them all wrong, you might want to review some of these major concepts before our next test. So here's a question for you. When does an object have more kinetic energy? When it's moving fast or it's moving slow? Now you probably answered that, oh, when it's moving fast, of course it's got more KE. And you are absolutely right. So there is a relationship between forces and energy. And remember, when we looked at kinetic energy, we looked at sound and thermal, and when we looked at potential energy, there was gravitational, elastic, magnetic, and chemical. Now, kinetic energies are the result of objects in motion. So what puts things in motion? Forces put things in motion. So potential energies are associated with a force between two objects. For example, gravitational energy is associated with the gravitational force between two bodies, such as the Earth and a ball. So there is a connection between energy and forces. So again, gravitational energy, it is caused by the force of the Earth pulling down on that apple. And think about chemical energy is associated with the electrical force between atoms. So there is a connection between forces and energy. Now let's look at this. And this will all be coming back around to the magnetic cannon towards the end of this video. So gravitational forces and gravitational energy. As the ball moves upward away from the Earth, it moves against the direction of gravitational force. So the ball's potential energy increases as it moves up. So if you took that ball and you moved it higher and higher and higher and higher, it's gaining more and more and more and more and more potential energy. So moving an object against the direction of the force leads to an increase in the energy associated with that force. Now, here's a spring. Does it work this way too? Yeah, look at this. Potential energy always increases as an object moves against the direction of the force associated with the potential energy. So when a spring is stretched, and we stretch it and we stretch it and we stretch it, it ends move against the direction of the elastic force, pulling the spring back to its original shape. So if you pull that spring out and you pull it and you pull it, or this could be a rubber band, you're pulling and stretching and stretching and stretching. As the spring stretches, its elastic energy increases. So again, you're going against the direction of motion there. So here's the magnetic cannon again. And we're going to use what we just learned about gravitational energy and the potential energy of a spring to help us answer some basic questions. Now, here's some things. We know that energy cannot be created nor destroyed. It can only be transformed or transferred. We learned that in the last book. Energy can move from one object to another, but it can't just disappear. It can be transferred from one system to another, but it can't just disappear. So if we assume no energy was transferred elsewhere, the total energy in condition 1, which was before ball A hit the magnet, must be identical to the total energy in 2. So what we're trying to explain is, where did all that energy come from that shot ball E out so much faster? Because ball A did not come in that fast. So why did ball E fly out so fast? Now, since balls B, C, and D have not changed their position, we know that their energy was not changed. So because these, and there's a little bit of a kickback, but these balls, B, C, and D, basically didn't move at all. So we can ignore them. Their energy, because they weren't changed, their energy was not changed. They did not move. So we're going to be able to ignore those. This means that the total energy for ball A and E in condition 1 needs to be identical to the total energy in condition 2. So what happens when an object moves in the same direction as the force, such as when a ball moves downward in the direction of the force? We know that the gravitational force decreases as the ball moves in the same direction. So if I drop the ball up high, and as it gets closer and closer to the Earth, the GE decreases and decreases and decreases and decreases, because it's all been transformed into kinetic energy. Correct? So do you remember learning that? Now, think about a magnet pull on a steel ball bearing. When the ball bearing moves towards the magnet, does its magnetic energy increase or decrease? So pause the video and talk about this with your group, or talk about it with an elbow partner. When the ball bearing moves towards the magnet, does its magnetic energy increase or decrease? So answer this based on what we've just been talking about the last 5 minutes or so. So go ahead, pause the video and discuss this, and then come back and hear the answer. So what did you come up with? Well, remember, moving against the direction of the force leads to an increase in the energy associated with the force. So it decreases because it's moving in the same direction as the magnetic force. So think about a magnet pulling on a steel ball. When the ball bearing moves towards the magnet, does its magnetic energy increase or decrease? It actually decreases. And this is hard for some people to understand, because you think, okay, if the ball's touching the magnet, it's hard to pull the ball off. But you're telling me that ball E, which is further away from the magnet, has more magnetic energy? Absolutely. Just like a ball that's further away up in the sky, away from the Earth, has more potential energy. Just like a rubber band that's stretched and stretched and stretched is getting more and more potential energy or elastic energy. Yes, so ball E, which is further away from the magnet, will have more energy. So as ball A moves closer and closer and closer to the magnet, it's losing its magnetic energy. So, in which case is there greater magnetic energy? When a ball bearing is touching the magnet, or when a ball bearing is at a distance away from the magnet? And the answer to that is there's less magnetic energy when a ball bearing is touching a magnet than when it's at a distance away from the magnet. So this is what we're going to do, and this is going to hammer it home. You're going to fill out this chart on the bottom of page 99. And you're going to fill it out by writing high, very little, or 0 in each cell. So condition 1. Remember, this was condition 1 right here. So you can pause the video right here so you can see it, but in your book, you'll want to be right here. So in position 1, or condition 1, the ball is here. So what potential magnetic energy? Is it going to be high, very little, or 0? How about kinetic energy? And then when we look at ball E right here, condition 1, ball E, is it going to have potential magnetic energy? Is it going to be high, very little, or 0? And then how about kinetic energy? So go ahead, pause the video and answer those questions. All right. So you've had a chance to do that. So let's look at condition 2. It's the other end. So ball A is already touching the magnet. So right now in condition 2, ball E, ball A right now, potential magnetic energy and kinetic energy. So look at where ball A is. Is its potential magnetic energy, is it high, very little, or 0? How about kinetic energy? Is it high, very little, or 0? Now go back and look at ball E right now. Ball A is already touching, so it hit, so ball E is ready to shoot out. And you can see there's actually a little gap here, so it's a millisecond after it hit. So does ball E have potential magnetic energy? Is it high, very little, or 0? And how about kinetic energy? Is it high, very little, or 0? So go ahead, pause the video, and answer these. And if you want to just put H for high, VL for very little, and Z or 0, a 0, a 0, right, is 0 for none, you can do that. All right, so here are the answers. So this gives it away. If you look at condition 1, they had a lot of magnetic energy, but as it got closer and closer and closer, when it finally hit, it was 0. But ball E has a high amount of magnetic energy in condition 1 because it's so far away, and the kinetic energy is 0. But look at this. Magnetic energy. So, okay, so if you go back up to condition 1, the kinetic energy, you might say, okay, it has a little, but at the ball, if you just really tapped it really slowly, it's not going to have very much. So maybe you put very little for this, and I'm okay with that. But then when you go to condition 2, it doesn't have any magnetic energy. It has very little because it's touching it. So it shouldn't have any. It's not moving anymore. Now look at this. The magnetic energy, because ball E is further away, it still has a high amount, but now it has all this kinetic energy. So when you look at it, here, there's just one high. But look at this. It has a high amount of magnetic energy, and it has all this Ke that transferred over. And the result of that, that's why the ball shoots out so fast. So, at the end of condition 2, only ball E has significant energy because it is both moving and it's far away from the magnet. So ball A, on the other hand, has almost no energy because it's in a motionless state and it's right next to the magnet. So you might say, it's got a very little amount because it's moving slowly. Okay, but it's next to 0. Because the energy at the start has to be the same as the energy at the end. All the energy that was at the start is equal to all the energy at the end. Since there's more magnetic energy at the start than at the end, the missing energy has to have been transformed into Ke. So again, there's high amounts in the start, and there's high amounts here. So all this Ke must have been transferred over here. That's why it shoots out so fast. So, since there is more magnetic energy at the start than at the end, the missing energy has been transformed into ball E's kinetic energy. And again, the reason ball E is further away from the magnet, which means it's going to have more magnetic energy, and that got transferred into the Ke. So write an explanation using energy considerations for why ball E shoots out of the cannon. I'm just going to go ahead and show you this. You don't have to write the whole thing down. Paraphrase it, please. So in condition 1, ball A has no Ke and a lot of Me, magnetic energy. Ball E has no Ke and a lot of Me. In condition 2, however, only ball E has significant energy because it's both moving, a lot of Ke, and it's far away from the magnet. So it's got a lot more energy. Ball A, on the other hand, has almost no energy because it's motionless at the very end, and it's right next to the magnet. So all that energy from A must have been transferred over, plus you have that additional magnetic energy because it's further away. from the magnet. So because the energy at the start has to be the same as the energy at the end, all the energy that was at the start is equal to all the energy at the end, kinetic and one's, a very high magnetic energy. Since there's more magnetic energy at the start than at the end, the missing energy has been transformed into the ball E kinetic energy. All right. Then question 2. The magnet in the magnetic cannon attracts the ball bearings just like the Earth attracts an object near it. Using energy considerations, explain why falling objects move faster as they get closer to the ground. Well, as an object gets closer to the ground, so its gravitational energy decreases. It moves in the same direction as the gravitational force. However, ignoring the transfer of energy into the air, the total energy of the object must remain unchanged. So if the GE is decreasing, then something must be increasing. In this case, it is indeed KE. So, make sure you guys watch the review videos for the test. Make sure you prepare for the test. Again, this is a hard concept. Am I going to have you explain all this in the test? No. But we did want to make sure you fully understand why ball E shoots out the way it does. So again, if you have any questions, just call me over and I'll do the best I can to help explain it. Thanks.